In this next video in the series, we're going to talk about the importance of nitrogen purge and nitrogen flow. We're also going to introduce a basic calculator that I kind of spun up in order to help us calculate how much you need to purge before you flow. Now, this is the first time I've ever done this, so some of you may see this calculator and may have some additions or changes or suggestions that you have for it. I'm always open to that feedback. But the basics are we always need to purge enough nitrogen to displace the oxygen before we flow. And we're going to talk about that and much more in this class.
I was going to talk through basically application, which starts to be what are you actually looking for, what do you do when, how important is it when, and what steps do you take actually in the field. I sort of asked some questions to guys, hey, when you are flowing, when is it easy to flow nitrogen, when is it not so easy to flow nitrogen, what are some things where you think it might be impossible to, and so how do we work through that? So we're going to go through best practices for application. The first thing is your piping, when it comes to the job, you want it to be capped. So if you have a supply thing come through, it's uncapped, it already has oxides built up, well, you're never going to get that back out. So send it back. They're supposed to send you hard copper shipped. So that's the thing. Anytime you open it or you look at a fitting or you go to put something, look through the pipe first. So you want to be looking through, making sure you removed both of the caps. They sit flush. You're making sure that that's not there. You're making sure we've all in this running service, you found weird stuff in a filter dryer or a separator or something. You're like, how did that get in there? Not sure how it got in there, but you'll find, I mean, on service calls, we found coins, you found screws, you find things that you're like, who in the world did this store? But it's easy to do. You have a bucket there, you have it, somebody dropped something in, you set it down for a second, somebody kicked something into your pipe. Before you actually dry fit a joint, you want to look through whatever it is and make sure you don't have something in there. So that's the first application. You want to clean your copper before cutting it. As you're cutting it, you're looking through, you're cutting that, you have the opportunity to get whatever's on that outside of the pipe into the pipe as you force your way through. So give it a sand ahead of time. It'll make it easier if you do it ahead of time to get your joint better anyway, because you've gotten rid of any of that oxides that fights your joining material. Once it's out, you're reaming it. You're getting rid of that little edge from when you cut it. You have an edge. Once again, this is where application is important. Reaming is important. It helps the overall flow, helps it not catch oil. But if you're looking at a pipe that's sitting straight up and down and you don't have any opportunity to get that sideways or down before you deburr it, I'm going to go ahead and say don't deburr it. The bigger evil is to drop that burr down in the pipe than it is to leave it attached to the pipe. And so a lot of that is to say being conscious of your application and what you're doing is the most important thing. Complacency is what kills things across the board. As soon as you become mindless. I do this all the time. I grab that piece, I put it in, I move on. This is what I do. And I know a lot of what you do can become monotonous, but that monotony and complacency becomes the killer. The thing that you didn't even realize you did, not where you made some conscious decision because of application. This is the best way to do that. Rarely is that going to be wrong. Everybody here's, well, most people here are intelligent people. And so if you're actually engaging your think brain,
I don't appreciate that.
If you're engaging your think brain, you can come up with the best application for what you're doing. It's when you do get in that, like, I'm here, I'm tired, I'm working, that's where really dumb things happen. In the pipe fitting side, even more so in the service side, you hear these stories. Matthew can tell you some stories from where he worked previously, where there's some stuff that you're like, how could somebody possibly do that? And you do that because somebody is just, you've been up a long time, you've worked a while, and you're doing a thing without engaging your think brain. And so that's a lot of what I'm going to go through. So you're looking through, you're making sure that they're dry, you're dry fitting it. In that same application is all the stuff we're not going to cover, but you're making sure your pipe is pitched back towards the rack. You're thinking through, hey, we followed the trapping practices for this type of refrigerant. You've read through all of your details on your prints to make sure the way this particular customer wants it is what you're following before you get going. Because once you're going, now you're going, right? And so, but you just get in that habit of every time you look through, you dry fit, you move on. Another thing I wanted to mention, because it came up a lot for bench fitting, when you're sort of pre-making a bunch of valves, is when you're working on a valve, if at all possible, you want that to be mid-seated. Meaning that you want it in that middle point, because if you compress the gasket while you're heating it, it doesn't take a lot of heat to deform that. And so a lot of times, if you're putting in a ball valve, put it at a midpoint. You're putting in an EPR, adjust it to a midpoint. CDST, even get your little tool out, pre-open them all to 50%. All the way back seated is compressed, all the way front seated is compressed. So anything that has a seal, you want that in its open state while you're getting it heated or unheated.
Yeah, and another key thing, and we're going to mention this, but the question came up about when you are bench fitting, so you're assembling valves. It's like, well, how do you flow nitrogen when you do that? If you think about it for about 3 seconds, you can figure it out, which is you can put the hose in the end and tape it off. You could come up with a plug that goes, it doesn't, you still flow nitrogen, right? And if it's really close assembled where you're like, well, I'm afraid it's going to melt my hose or whatever, well, then wrap a rag around it or something. But you still want nitrogen flowing through that valve. Cleaning it later, cupric oxide just doesn't come out easy. If you've ever tried to do it, it's a pain in the butt to get it out. The only thing that you're not going to probably be able to flow through would be like a hermetic compressor. So if you've got, maybe you're working on something smaller and you're working on a hermetic compressor, you're not going to flow through a hermetic compressor, obviously. But you can still displace as much as possible. We're never going to get 100% of the oxygen out. We're not even trying to, but we're trying to get as much of it out, displaced with nitrogen as we possibly can. So be creative if you have to.
Yeah, and so the thing that I always want to say is don't let an ideal perfection get in the way of doing the best that you can right now. And so you're doing a whole new store where you're pipe fitting. The application is perfect. You get it all set up, you purge. I think there's the next slide has the purge on
First,
it.
we want to show just quickly, this is the reason why you deburr. And it actually does matter more in market refrigeration than it does in a lot of other spaces because that turbulence builds up. So like Nathan said, it can gather oil, but also it actually does present resistance. So you get turbulence on the other side of a non-deburred section. But we don't want deburring to become a bigger problem because we're dropping copper shavings, right? And just blowing some nitrogen afterwards isn't going to get rid of 500 feet of copper shavings that you leave in the tubing. So we don't want to create a problem while solving a problem, but deburring is a nice standard practice, and they make tools that kind of really easily, those circular deburring tools. Some of you use the old pencil type. But deburring during pipe fitting, it's a step that gets missed a lot in the industry, but it is a good best practice and does help with oil return.
No, and you can tell, you'll even hear sometimes a loud circuit. Now sometimes that can be that the gas is flashing in it, and so that might not always be the case, but there are loud circuits. And it usually is that there's some sort of irregularity there, so you're not getting a laminar flow through it, so you'll hear refrigerant moving, and a lot of times that is that the burr is pretty good in there. Yeah, I mean, so now we're kind of going back to, this slide is just sort of about when you're inserting it, the rule of thumb, which I never actually thought about, but that until I was, why are different size couplings different depths? And it's just for strength, you want that insertion to be about the full dimension of the pipe. So your coupling will be twice as long as the dimension of your pipe. And that's just for pipe size, strength, whatever, that's there. You're trying to draw that, the alloy, correct. You're trying to draw the alloy in there, not all the way to the center, but you're trying to get at least, half of that fitting that it's on. You're wanting to see that discoloration of drawing the alloy in that far. That tells you have penetration. And same thing where you're saying the capillary action, you need a certain size gap. That's basically just saying use the right size coupling for your pipe. Don't, hey, I'm out, so I'm going to put too big of one and crimp it down. Or I'm going to do an inside coupling, so I'm just going to take a smaller pipe and put it in. Like, if you're using the right size coupling for the right size pipe, your gap is going to be correct. But same thing if you have a bent piece of pipe and you're like, well, it fits and I can fill that gap. Just go ahead and let's cut it back past that bent piece and get a good fitting there, particularly when you're doing a new line set, new store, so there's no time constraint. Let's go ahead and get it correct.
It's counterintuitive because a lot of people think bigger gap means you'll pull in more solder. It's not. The tighter the gap, the more capillary action. That's how capillary action works. The smaller the channel or gap, the further it will actually draw in.
Right, because this isn't like fitting PVC, where I've had guys say that, well, like if you have it too much, you'll scrape it off. Like it's not glue. We're not gluing the fitting. You really do want it tight enough that it'll take some force to get it in, but it will fit. And so same thing about being cognizant. You ever push it in and it just doesn't feel right? Like it goes in real easy. Maybe take a minute and think through. Maybe you have a plumbing coupling for some reason. Maybe something's wrong. Like you should get used to it. Takes some force to get those seated. So this gets us down to the meat of what we're talking about, which is flowing nitrogen. And I wanted to go through, this is kind of telling you how to do it. which everybody should know the basics on how to do it, but I'll also walk through some terms, right? Because guys will use just different, I've heard people say, oh, well, you purge nitrogen while you're brazing. Fine if you say it, but it's not the correct thing to use. Purge is while you are displacing oxygen. You're getting all of the air out and getting it replaced as much as possible with nitrogen in there. Then you're backing it down to flow, which is you're still adding some, so you're in higher pressure than the atmosphere, so air doesn't come back in what you just flowed out of, what you just purged out of. And so this was actually an interesting thing where we were like, hey, we need to actually get a recommendation for how much purge to go. Because up until now, you've always just told people, well, purge till there's no air. That's the end. And so then I was thinking through, though, well, like, how do you know? You know, it's pretty easy if you're doing a 4-foot piece of pipe or a 20-foot piece. But what if it's 500 feet of 3 1/8 inch pipe? How much purge do you need before all of that's out of there? Looked through, actually didn't so much exist. Like anything that told you how much to do, all of it pretty much just said, well, do it until the air's gone. Well, that doesn't work for me because it doesn't tell you anything. So we built a little calculator. It's in your form. There's a download for it. You can find it later. But you can punch in your feet, how much whatever, and it'll tell you how long, at what pressure should you purge, and how much of your tank is that going to use. And so you sort of have an idea. This is how much got out. After that, it gets easier because how much should you add once you're brazing? Just enough that no air can come in. Like that part's pretty easy because you put some tape over the end, you poke a hole. Can you feel air coming out? You're good. Can you not feel anything at all? Like you put your hand over it and you don't feel anything? Well, then maybe you're losing a little bit through the joints and you may need to increase it.
That's a really important distinction. We're not pressurizing, okay? We're flowing. That's why we use a flow regulator, not a pressure regulator for flowing. We don't want to pressurize. Of course, there is a pressure differential, but like Nathan said, it's infinitesimal. It's tiny. We do not want to pressurize. Pressurizing causes your joints to blow apart when you're trying to braze them. You want a tiny flow, 3 to 5 SCFH, which if you want to be really technical, that's exactly 1 gnat fart worth of pressure. So it's scientifically proven. Whereas when you're purging, that's when you open that regulator up. The math that I did for this calculator is based on a, what is it based on? It's based on 20 to 50 SCFH of flow for a typical nitrogen regulator. You're going to have some regulators that are going to produce more than that, but I'll give away the lead here. We've got to purge a lot longer than anyone ever thought once we did the math. It can be a long time. It can be like 5 minutes in some cases of purge, where you're leaving that thing open, you're setting it to 100 PSI, and you're just letting her fly. And who knew, right? You look at all the books, manuals, nobody tells you. Like Nathan said, they're just like, just till the air's out, right? So just took a little bit of math. That's why we created that calculator. Because my assertion is a lot of times on long runs where you're like, I know I flowed nitrogen. Now, there are cases where we didn't, and that's the bigger issue. But you still find issues. I think that is the thing. We did not do a thorough purge. Because once you go to flow, you're barely moving any nitrogen through those lines.
No, I mean, so the same thing on an application where you're doing new line sets, new store. Everything's isolated. You can be pretty aggressive with your nitrogen because you're not going to cause a problem. And once again, like you said, nitrogen is not a significant expense. So I love to see more nitrogen than I thought a job should need ordered and sent back empty. That makes me feel good, where less does not make me feel as good. So I'm not telling you, I will never tell you save nitrogen. Now this is where I say application. If you're doing a case change or repair or something like that, so it's an existing system, you want to be a little bit more careful. So whatever you're purging, whatever you're flowing with, you want that pressure below whatever the pressure is on the opposite side of the valve, because pushing nitrogen back into your live system is going to cause more problems than any amount of other abuse over here could cause, which is not saying don't do it. What it is saying is you have to engage your think brain. What is this rack running at? Okay, I'm brazing on the low pressure side. It's 5 PSI. Okay, that's fine. I just have to make sure this pipe never achieves more than 5 PSI because it's not going to suck back to a higher pressure. The only time where you start to get a little bit iffy on it is if you have a rack super low temp or something that's running in a vacuum. At that point, I'm going to recommend you keep it separate while you're doing all of your brazing. Then displace the nitrogen. Same thing. When you go to do it, if you're on that last joint where you're like, man, I'm not comfortable putting nitrogen, I might be putting it back in, you're going to displace all the nitrogen, blow it all out, get it there, dry fit it, braze it right away. The oxygen's out. It's not coming back in that fast. So you've never been under positive pressure. You've still gotten rid of the air that's in it. which is to say some guys will be like, well, is that then perfect? Maybe not, but it's really good. And the other option is to just not do it, and that's what we're saying is that isn't an option. So same thing in that application where you're pushing that last fitting and connecting right to a reciprocating compressor, where there's no way that you can flow nitrogen. If you do, there's a chance of getting some bigger problems caused. Same thing, let's blow nitrogen in it, let's purge it before we connect it, blow it in the side that we can't, seal it, braze it up. Because there isn't, you're just getting to that application. Same thing on bench fitting. They're like, well, this is so huge, it's open. Put tape on both sides. I'm not saying you have to braze in a port. Tape around your hose, put it in, then poke a hole in the other end. If you can only get on this side, poke one hole on this end. It doesn't, you're just keeping it in there while you're under positive pressure. Air's not gonna fight back past positive pressure. And so if you're doing that, you're going to keep the air out and you're not gonna see that burn.
So the point is, don't risk pushing nitrogen back into a rack. That's not okay. It's also not okay to not flow nitrogen under any circumstance. Does that make sense? Pretty clear.
No, and so here you have the example of flowing nitrogen versus not flowing nitrogen. There's some, yeah, I mean, it's just a nice little demonstration of that happening. But all of that is to say that application is, it changes, it's there, but if you are actually just thinking through, okay, what's the best way to do this, it's not actually difficult. And so you do have people, you do have some objections there. They're usually a fake objection. It's just an objection because it's difficult or I don't know what I'm doing on it. If you feel that or you hear somebody saying that, stop, engage your actual think brain, work through it. It's not difficult to figure out a way to get to a very good end result without a lot of cupric oxide.
Another thing your old-timer buddy used to say to you is some version of, well, I don't have to do that because I don't get the, I just make sure not to get the pipe too hot, because those flakes happen when you get the pipe too hot, right? Well, those flakes also happen on the inside when you get the pipe hot enough, because if you don't get it hot enough, yeah, you could seal the edge and not end up with a lot of cupric oxide on the inside, but you didn't actually pipe fit properly, right? So if you are pipe fitting properly and you are not flowing nitrogen, you should have a crap ton of cupric oxide on the inside of that pipe. Do you understand what I'm saying? So if you're not, it means you're not getting hot enough. So it's okay for that to happen, but it's not okay because you should be flowing nitrogen, right? So you got to do both of those things. A lot of people believe that the black stuff comes from your torch. Again, it does not. It comes from the interaction between oxygen and the copper. We should not be afraid of getting things hot enough for cupric oxide to build up. We should absolutely prevent it by flowing nitrogen.
No, I mean, and you'll see when we go over and do the actual bench test, it's not iffy, right? If you flow no nitrogen, it is very obvious that no nitrogen was flowed. So those of you who are like, oh, well, you know, I do it a little, it's not. I know how the results will look. It's not like, oh, maybe. It's like, no, there's no doubt. It's pretty, the maybe happens if your tank was running out or you didn't purge quite enough or you did like that. That can be a maybe. The did not flow anything, I don't care if, and you get some pull in, it doesn't matter how good of a pipe fitter you are, it looks surprisingly bad. The first few times you did it, you're like, whoa, that was way more than I thought. So it's not really that complicated. I mean, same thing, best practice is protecting heat-sensitive parts. It's not complicated. Once again, mid-seat your valves so they don't compress. If there's something that has something on it that isn't metal, so it's anything that has a gasket, anything that has whatever, just don't let it get hot enough to melt it. That's the end. And people will be like, well, what does that look like? It just looks different for different applications, but you kind of know. Right, you can wet rag it. They have good putties and stuff you can use now if you can't use wet rag. You can see he kind of protected his valve so that there's not going to be bleed by to his, it's an accumulator. And so it's one of those things that guys will, sometimes you'll hear guys act like, oh, well, I overheated it, but I was protecting it. And like, no, you weren't. You weren't. That doesn't, it's not hard to keep it cold enough that it doesn't melt. Once again, perhaps if you have a valve really tightly seated, then it doesn't take a lot of heat. But if you're following everything you should, it doesn't really happen.
Be cute with your heat. Protect the parts, right? So a lot of guys are trying to be cute with their heat because they're not protecting the components. If you're protecting the components, then you can get the joint hot enough to make sure you draw in via capillary action. Make sense?
So we actually have charts, we have information that you can go back and reference. This is not an in-depth class to teach you every tiny little thing about brazing. This is to show you that where the information is at so that you can do the homework, right? Brazing is intentional, guys. When we're going out to the field, when we're selecting our brazing alloy all the way to the actual base metal that we're going to be brazing, we have to be intentional with our design, with what we're setting up here, between the copper connections to torch tip selection. Does anybody know the two things that we should know that we have to go by to select the correct torch tip? Those two things are what determine your torch tip selection is piping diameter and application. So when we talk about application, we talk about clearances. As everyone knows here, some of you are service technicians, right? There are certain applications where you can't get a full-size torch tip for the diameter pipe that you need in a low access area, whether that's inside of a mechanical closet, whether that's in a cabinet, whether that's in an elevator shaft, underneath, beside a compressor, right? We've all been there in those situations. There are specific torch tips that are designed to apply, as you can see here in the demonstration, and it's the Captain hook, right? Rightly named because it looks like a hook, that allows you to apply the same amount of heat with just multiple actual orifices to create that heat that you need, which you normally would get with a rosebud tip or a standardized tip. Now back to the first part, right? Tip selection is based upon piping diameter. Now you'll notice at the base of every single torch tip, there is a number. That number is a manufacturer's number to reference the orifice size at the end of your tip. The tip selection is designed based upon the actual diameter of your pipe to apply the correct amount of heat that you need to get that joint as hot as it's supposed to be, right? 1300 degrees to melt your alloy and to actually bring it in with that capillary action that we talked about. What happens when I select a tip that's too small? I spend a lot of time brazing, as I've heard it in the industry called. When you're building stalactites and stalagmites, right? We're not building sandcastles here. We're trying to heat the joint to a specific temperature to actually get that alloy to become a liquid. Not only a liquid, but flow freely within the joint that we've cleaned, that we're purging with nitrogen. When you select a tip that is too small, you're going to find that you're going to inadequately heat the actual copper fitting itself, and you're going to build a bead across the top surface there, and that is not the correct application. You'll find that through vibration, through movement in that pipe, that'll eventually lead to leaks, if not at that point of time pressure testing, but over time, it will create leaks, right? We're joining, not repairing, as Brian said. The other side of that, what happens when I select a torch tip that's too big? What that results in unnecessary fuel usage, right? As everybody knows, our fuel is in tanks. Those tanks only hold a specific amount of fuel. If I choose a torch tip that is 3 times larger than the pipe that I'm going to be brazing, instead of being able to do 20 joints in an hour, I'm only going to do 3 because I just emptied my tanks trying to hit that specific goal. Now, I get that going through this, right? And as you can see, we built a chart here. You don't have to have every tip they make, but you should have enough to cover each piping diameter that you may be working on, whether that's 5 inches all the way down to 3/8, quarter inch, or even capillary tubes. You'll notice here the important thing is those, like I said, those numbers, they're imprinted on the tips at the base. If it's 00, 0, 2, 4, you'll also notice here we have rosebud tips. Rosebud tips are designed for larger pipes. The 2 things to remember here, guys, we selected off of piping size, and then we're also going to ensure that with our regulators, we are setting the correct pressure for oxygen and acetylene. We have 2 fuel sources here to make this happen. Every tip is different. Based upon the tip size that you have will determine how you set your oxygen and acetylene rig to the correct pressure so that you get the correct amount of heat. This is a long step process, right? You understand it in the field after you go through it numerous times. And most of you technicians already have your favorite tips. You have your tips that you know exactly what they should be set to and what application they apply to. And the last thing we talked about, right? That's that acetylene consumption, that fuel consumption. You'll notice here as we get to a larger size, 0, 1, 2, 3, 4, 5, that acetylene consumption, the SCFH goes up, right? Your tank only holds a specific amount of volume. If you need these numbers, you can find these numbers, right? Uniweld does a great job of documenting this on their website for every tip that they make. There are 17 different types of acetylene and oxygen torch tips that look like this for brazing and soldering. And there are a vast majority of other tips, rosebuds, you name it. So, all right, setting oxygen and acetylene pressures. You'll notice here on the tanks, left-hand side, as you're looking at the tanks, is your actual pressure for your hoses. The right-hand side is actually the gauge for the volume of gas or fuel left in your tank. So left side is hoses, Right side is tank pressure, whether my tank is full, whether my tank is empty, whether my tank is a quarter full. That's all determined here. Now, one thing I can't stress enough, safety. It doesn't matter if it's your torches or somebody else's torches and you use them every single day. You should be, anytime you go to braze and you go to turn on your tanks, right, because you're leaving them closed when you walk away from them, you leak check. Leak check, leak check, leak check, leak check. I have seen some pretty nasty disasters in my life in this field due to skipping that step. Things happen when you're not around, guys. Tanks fall over, someone knocks it around in your van. If they're not yours, right, it's all the more reason to go through these checks. Like Brian said, with don't oil the oxygen fittings, right? It's the same thing. When you pressurize your tanks and your fittings, you want to check your regulator as well as your torch handle. Last thing you want to do is braze something and come to find out that your acetylene is leaking from your rig. Lord forbid it doesn't ignite, but you only get one fitting in before your tank's completely empty, right? It's all happened to us. We've all been there. Safety, safety, safety. All right, so let's talk about flames. So we've talked about torch tips, we've talked about fuel consumption, we've talked about how to select the correct torch tip for your application based upon piping size as well as application. Let's talk about flames. There are 3 different types of flames. There's carburizing, there's neutral, and there's oxidizing. Easy way to remember this, guys, I can go through the scientific explanation of them. Carburizing is too much acetylene, right? We've got a flame tip that isn't actually combusting all the acetylene that we're expelling from the torches itself. What does that do? That actually causes a chemical reaction with the surface of the base metal that you're not aware of, right? That's that excess oxidation. It's not the cupric oxide that we just talked about, right? It's actually something completely different. Let's talk about oxidizing. We broke down the word oxidation, right? It's the same thing. Oxidizing flame is too much oxygen. It's excess oxygen at the end of your torches to where it's not being combusted. So what can that do? Why is that bad? When we talk about brazing a joint, we talk about brazing a connection, we are flowing nitrogen. But at the time of starting that braze, our flame direction into that joint, onto that male side fitting, down into that coupling, right, is forcing that heat down in there. You will find that there are rare scenarios where an oxidizing flame will actually cause that cupric oxide to build up inside that joint because of the excess oxygen, because of the torches being set up incorrectly. So what we like to say is you want a neutral flame. It's also, you guys have probably heard in the industry, is natural flame. A slightly carburizing flame is okay, but I preach neutral flame all day long. And that is a large secondary flame and a small primary flame, right? You can also tell someone who has an oxidizing flame because the torch is very loud. It sounds like a jet engine, right? If you can hear the jet engine, you're not doing it right. Go back to the drawing book. Look at your torches, adjust them accordingly, and make the change. This stuff matters, guys, because if you're burning your torches, right, a neutral flame is a balance 50-50 of oxygen and acetylene, right? Carburizing flame is too much acetylene, you're going to run out faster. Oxidizing flame causes oxidation as well as running out of oxygen before it's supposed to.
And let me mention real quickly here. So when he talked about setting the regulators, look, I know common practice in the field is for people to do most of the regulation at the handle. But if you're trying to maintain a neutral flame, that's where that becomes really tricky if you're not close from the regulator, right? You've all done this where you're brazing and you accidentally bump the knob and it makes a massive difference in the output. That's why, because you're doing the regulation at the knob. If you're doing the majority of the regulation at the regulator, then if you turn the knob a little bit, it only makes a very slight change, which makes it much easier for you to maintain a neutral or near neutral flame. To the point of oxidizing, it's not just about, again, this is obvious, right? Oxygen bad, right? We all got that. It's not just about getting it inside the tube. When you have an oxidizing flame, it actually creates more oxide buildup on the outside as well, which interferes with your making a connection. Anybody here ever weld? And you use like shield gases on the outside of a weld? Well, shield gases, what you're doing is you're displacing oxygen from the outside. When you use an oxidizing flame, you're introducing oxygen to the outside, not desired.
No, that's a great point. So we talked about it before, guys, but when we talk about brazing and technique, right, we've talked about torch tips, we talked about torch tip selection. When we're brazing the pipe itself, we want to heat the male in first, right? That heat is going to traverse the joint down into the actual connection itself. We heat the male part first, and then we work our way down to the coupling. Remember, the point of this process is not to allow the torch flame to melt our alloy, right? If we're melting alloy with our torch flame, we are doing it incorrectly. Your base metal should be hot enough to melt the alloy on its own. if you have correctly preheated the pipe, right, male in, down to coupling, and you get to the correct temperature, which we're going to show you here on the next slide, of that dark cherry, medium cherry color, you will find that you don't have to do any additional work. That when I have touched that alloy and that alloy begins to equalize temperature with the joint, it melts right away. It becomes liquid very fast, right? Our alloy actually melts around, 1,190 degrees, right? Ideal temperature is 1,300 degrees, right? That's when it becomes a full-blooded liquid and is going to flow through that joint and fill that joint like we're looking for, which we talked about here, right? These are the temperatures that we're looking for, that medium cherry to cherry. Now, I was taught, right, the wrong way very early on. I've been in this field for a very long time. It doesn't look like it, but I have. I'm third generation. My grandfather, my father taught me the same thing, right? If you get it to this cherry color, you've overheated it. I need it at this cherry color to melt my alloy. If it's not this cherry color to dark cherry color, it's not going to melt. I'm going to rely on this to melt it, which is incorrect. I'm going to create a bead across the top. It's not going to fill the joint. We're not going to actually be joining anymore. We're going to be repairing. That leads to leaks, cracks from vibration, pipes blowing apart, right? We don't want any of that stuff. So we're joining here, right? And all of this is intentional. It's doing your homework, doing your research, understanding what you have, what you're using, and when to use it.
Yeah, the temperature indications apply across essentially all of your base metals other than aluminum. So unless you're doing aluminum, you can always rely on this temperature guide. If you're doing steel, if you're doing brass, they're still going to do the same thing. So if your alloy is kind of a 1,200 degree alloy, well, then you got to get it above dark cherry. Yep. If you're only getting to dark, if you never get that whole fitting to at least medium cherry, you didn't pull alloy in all the way.
Nope.
And that's really common in the trade. And a lot of it, like I said, is because a lot of people come up through residential or like commercial where you can get away with a lot. You can put just a little cap on top and it's fine. But if you're working near a semi-hermetic compressor that's on suspension and you have really high temperatures and a lot of load variation, you're going to find out real quick whether you were good at brazing.
Yep. Copper is not, it doesn't break the rules of physics, right? So as it changes temperature, whether it equalizes to room temperature or goes down to 30 degrees or 15 degrees, that copper will actually expand, right? It moves on the racks, right? That's why we don't grab our copper, rigid copper, horizontally. We have to have that room to actually move. And then the more so that's in VRF. But common issues, right? Underheating issue, right? Doesn't pull into the joint, bead across the top. We've talked about those issues. Overheating the joint. We touched on overheating in regards to, yes, it's bad, right? You blow a hole through a pipe. Let's talk about the other downside. When you overheat a pipe, you change the physical characteristics of that pipe. It's no longer a round hole, it's an oval hole. If there's any kind of weight, any kind of pull on that line, anything that's pulling it in a different direction, when you overheat that pipe, it will actually change the physical properties of that joint and it will now become too large. And then you go to braze it and then you're sticking 5 to 6 rods into it, right? It's just pooling up inside the pipe. Or Lord forbid you overheat it to the point where there is a little bit of pressure on it and it pops apart, right? Overheating, just like underheating, they're both just as bad. And last thing, right? Poor penetration. We talk about actually fully inserting your copper tubing into whatever joint it meets, whether it's an elbow, whether it's a coupling, right? You want to make sure that it's fully seated to the backside. We are not just sticking them slightly together and hoping it holds, right? It's only as strong as its depth, which is the same diameter of the pipe and should be. So